So 12.7 deals with analyzing empirical data. And so here's the situation. We assume we've somehow managed to take a random sample of size, some size, say n, and so we get these n measurements. X1, xn. And since our sample is truly random, as these measurements as random variables should all be independent of each other, and they're identically distributed somehow. We don't know how, with mean mu and standard deviation, that's a standard deviation sigma. Where typically we don't know mu or sigma. Our goal is to find out something about them. And so last time we talked about the sample mean. Simply the average measurement. And we know from the central limit theorem that this will be normally distributed, almost. Its expected value is mu, which we don't know. Its standard deviation, sigma over the square root of n, which again, typically we don't know. And we talked about the sample variance. S squared, and as with the variance before, we have two equations for this. We can look at it as the measurement minus the mean measurement squared. And then we average these up to see what the square of the measurement minus the mean looks like. Minus x bar squared. We average them up almost, except instead of dividing by n, we divide by n minus 1. And we had another equation, an equivalent equation for s squared. We look at the square of the measurements and average them up, sort of, except we're dividing by n minus 1 instead of n. And subtract the square of the sample mean. Yeah, but with a fudge factor that's close to 1. And we talked about the sample standard deviation. Simply the square root of the sample variance. And the expected value of s squared is sigma squared. So we figure this ought to be close to sigma. And then we talked about the standard error. d s over the square root of n. Now, the sample mean has standard deviation sigma over the square root of n. And so we figure this ought to be close to that. Well, that's where we were last time. Now we want to look at confidence intervals. So here's what we want to do. We figure x bar should be close to mu, but we want to be more quantitative about that. We want to make statements like the following. We are, well, some percent certain, confident that the mean of these measurements, the thing we don't know, is in some interval. And that interval will be centered at the sample mean. So it will be x bar minus something up to x bar plus that same thing. And we want to know how to fill in these two blanks. Okay, well, to see how to fill in those two blanks, we apply the central limit theorem. So over here, let me move the boards around. Let me tell you how to fill in the blanks. Well, the probability that this unknown mean mu is in the interval, some interval some interval centered around the sample mean. So it's x bar minus some quantity, call it epsilon, up to x bar plus epsilon. Here's the picture. That's the real line. X bar is somewhere. So we're taking an interval of length 2 epsilon centered at the sample mean. So we're looking at this interval from x bar minus epsilon up x bar plus epsilon. We're looking at that interval. It's 2 epsilon long. And we want the probability that the mean is in there somewhere. Well, central limit theorem lets us say something about this probability. First, let's rewrite this to say that mu is in this interval is to say that the distance between x bar and mu is no more than epsilon. Right, so that's just rewriting. Now we use the fact that x bar is normally distributed, almost, and we want to standardize. So we've already subtracted x bar's expected value. So we don't have to do that. What we have to do is to divide by x bar's standard deviation, which is sigma over the square root of n. Okay, so on both sides of this inequality, we divide by sigma over the square root of n. well, it's a compound fraction. It could be written better. Because now we have a random variable with a standard normal distribution. Let's call it z. Okay, so here we standardized by dividing by the x bar's standard deviation. And now we apply the central limit theorem. We have the standard normal distribution. The probability that a random variable with a standard normal distribution is less than or equal to some number, call it little z, where little z is well, it's a compound fraction. Let's write it better. Epsilon square root of n over sigma. Well, why do we want to know that? It gives us a result like this. To say this again, we found that the probability that mu is in the interval x bar minus epsilon, well, we can write epsilon in terms of this quantity z. Solve this equation for epsilon. It's z times sigma over the square root of n. Okay, so we had that probability that the mean mu is in the interval x bar minus epsilon, so we have z sigma over the square root of n, up to x bar plus z sigma over the square root of n. The probability that mu lands in this interval is the probability that something with a standard normal distribution, well, we know all about that, is between minus z and z. It's a picture that we're going to think. Here's the standard normal density. We'll be looking at the probability that a random variable in magnitude, that is an absolute value, is no more than z. The probability on the right-hand side here is that blue area. Or to say this somewhat differently, we want it to look like that goal over there. And then we'll put in the probability here. Our degree of confidence is this probability. So we'll put that in for one blank. And if little z is large, this will be pretty close to 1. I mean, large, but if z is 2, this probability is pretty high. That mu is in this interval x x bar minus, and to fill in this blank, well, it's z standard deviations down, c sigma over the square root of n, to c sigma. Well, we'll refer to these intervals as confidence intervals. And yeah, sometimes we'll want to look at it. We have this equation between probabilities, but sometimes we want to say it like this, that we'll refer to this as a confidence interval. Yeah, but how confident are we? Well, that's going to be given by this number. And we will choose different values for z depending on how big we want this to be, and that will affect how big this interval is. It's an interval centered at x bar, and it's 2z sigma over the square root of n log. Well, so if we want the interval to be short, we'd like to have a large sample size here. Now, what to take for z? Well, it depends on how big we want that probability to be. Let's make a chart. Well, if we're willing to this probability, say, to be only 68%, try taking z to be 1, little z to be 1. And then we look in our table, phi of 1 point 8413, I think. Handwriting is not. And so that tells us that something about this area, the right half of it would be 0.3413. And so the whole thing is twice that, about 68%. 0.34 doubled. But if we want to do one or two more of these, suppose we want 95% confidence. Well, then we work backwards. So what z value would give us 95%? Well, we'll need phi of this to be 0.975 because that includes the left tail. If this area in the middle is 95%, the two tails account for the other 5%, 2.5% each. And so we look in our table, what number gives phi value of 975? 1.96. It comes closest. Well, let's do one more. What if we want 99% confidence? Okay, so we need a z value, phi of which is 0.99 plus the left tail. So the two tails together are 1%. Each tail is 0.5%. So we need a z value 995, and the closest, we look in our table to two decimal places, it's 2.58. Trouble is, as wonderful as these are, they're going to be useless when we don't know sigma. But we know S from our data. And so this is the confidence interval we get if we use sigma, which is fine if we know sigma. Maybe we don't. But for a reasonably large study, we figure S ought to be close to sigma. And here we have sigma over the square root of n. Instead, we'll use S over the square root of n, which is nothing but the standard error. Can be replaced, yeah, with some error, but these are all approximations anyhow. S over the square root of n, which we recognize as the standard error. Well, so our conclusion again a variant of it, the probability that mu is in the interval x bar minus z standard errors up to x bar plus z standard errors is approximately, because we're using the central limit theorem, first of all, is an approximation. X bar is almost standard, normally distributed. And we've introduced some other approximations since then. The probability that a random variable with the standard normal distribution in magnitude is less than or equal to z. That is, we have a certain degree of confidence, and we can say what that degree is. If we want 99% confidence, we'd better take our z value of 2.58. That the mean mu that we weren't given but we're trying to find out about is in this interval. Sample mean minus z standard errors to x bar plus z standard errors. That is, we fill in the other blank with z standard errors. Well, the same equations, but in place of sigma, using the sample standard deviation. And this is also referred to as a confidence interval. And of course, it's 2z standard errors long. So to get, if we really want to know pretty accurately what mu is, we'd like the length of this to be fairly short. Well, let's see how this plays out in practice. Going back to the example from Monday, we wanted to know something about the number of objects in a student's backpack, and we took a random sample, we imagined, of size 10. So we got these 10 measurements. Well, here they are again, the same numbers. The largest was 47. The smallest was 0. Yeah, but they're kind of spread out. And if we add these up, we get 162. So the sample mean was 16.2. And the sample standard deviation was 13.4. So the standard error would be 13.4 divided by the square root of 10. Now let's set ourselves the following problem. Find a 98% confidence interval for mu, the true mean number of objects in a student's backpack. A number we don't know, but we figure it's somewhere around 16.2. Our rather small sample here, it's pretty spread out, 0 to 47. But this sample gave us an average of 16.2. So we want this confidence interval. By what did I say? 98% confidence interval, I mean, I want this probability to be 98%. So as step 1, we find what the z value is. Probability that something with a standard normal distribution is less than z value in absolute magnitude. That has to be 98%. Well, it's not on our table here, so we'll have to add one more line to our table. If this area is 98%, then phi of z is what? Well, this thing in the middle is 98%. The two tails together make up the other 2%. So each tail is 1%. So we need phi of z to be the 99%. 98% plus the left tail. And so we look in our table to see how close we can get to that. And 2.33, the 2 decimal places, is the number that comes closest to 0.99. It gives 0.9901. Well, that's really close. So, secondly, we make our confidence interval, and it goes from the sample mean down z standard errors and up z standard errors. Sample mean was 16.2. We're going down z standard errors. And up by the same amount. Well, so then we do the arithmetic here. Z standard errors turns out to be close to 10, not quite, about 9.9. So here we are with the interval from 6.3 up to 26.1. This is our 98% confidence interval for the mean. That is, we're 98% confident that mu is in this interval. Well, that's not a terribly impressive conclusion, because this interval is pretty big. From 6 to 26, it's nearly 20 units long. And the defect is that our sample size of 10 is just not big enough when the numbers are this spread out. We haven't narrowed down a whole lot on what the true mean is. Yeah, we were 98% sure it's in this interval, but this is a pretty big interval. One way to make the interval, well, there are two ways to make the interval smaller. The interval depends on z and the standard error. We could make z smaller, yet we could make n larger. Okay, well, let's look at the first of those. And if all we have are these 10 numbers, we're kind of stuck with n equals 10. Let's try to find, say, a 90% confidence interval. Well, that will be a little shorter. How much shorter? Well, let's try it and see. Step 1. we find the z-value. Well, 90% isn't on our table, so we have, our table had 3 lines there. We have a 4th line we can add to it. Now we need a 5th line. We need a z-value so that this center area will be 90%, so the 2 tails make up the other 10%, 5% per tail. So we need phi of z to be 95%. Well, so we look through our uh, 90%. Our table, what number could we put into the table to get 0.95 out? And the thing that comes closest is 1.64. Well, it's actually a tie, but phi of 1.64 is almost 0.95. But not quite. So that's our z-value. And then secondly, we can use that to make our interval. (16.2) minus, okay, our z-values, we have 1.64 standard errors. Sample mean plus that same number of standard errors. So we do the arithmetic. It's the interval from 9.2 up to 23.2. Our 90% confidence interval. Yeah, it's shorter than the 98% confidence interval. It's still pretty big. If we really wanted to focus more tightly on mu, we'd need some larger study. Now, a special case of this is where the measurements are binary. So the things we've been saying so far apply whether the measurements are binary or not. But let's look at to see if there's anything extra we can say if the random variables, the measurements we're doing are binary. That is, we take a random sample of size n as before. And we get these n measurements. But the measurements are simply 1 or 0. Yes, the person has the disease. No, the person does not have the disease. Yes, the eighth plant has genotype little c. No, it doesn't. Yes, the cholesterol is high. No, it isn't. And they're all identically distributed and independent. So we get yes with probability p and 0 with probability 1 minus p. We don't know the true probability p, but we'd like to get a good idea of what it is. In fact, we'd like to say with a high degree of confidence that it's in a certain interval, and that's what this work lets us do. So we get these n binary measurements. If we add them up, we're just adding up zeros and ones. Well, the zeros don't contribute anything. So we just get the number of ones. The number, we call it k, of successes. If thinking of 1 as success and 0 as failure, we add them up and we get the number of ones. So our sample mean, k over n, is the proportion of successes. Following the book's notation, let's call that p hat. It should be close to p, right? We know that the expected value of x bar is p, and the expected value where x bar is p hat. Yeah, so these should be close, but how close and how confident are we? Well, we've worked out. Let's copy over some of the things we've said about our confidence intervals. The probability that the unknown probability p is in the interval p hat minus z standard errors up to p hat plus z standard errors is approximately, because we've made a couple of approximations here, the probability that something with a standard normal distribution is equal to z. Well, that's just sort of saying the same thing we said before. We have this much confidence that p is in our interval p hat minus z standard errors p hat plus z standard errors. Old hat, right? The same thing we've said on the other boards. But one new thing we can add is we have a simpler calculation for the standard error. That works for binary variables. So let's put that down. So what's new here in the special case of binary variables, that the standard error, well, we know that's s over the square root of n. P hat times 1 minus p hat divided by n minus 1. We want the square root of that. Now, let me tell you where this comes from. We know what the variance of a binary variable is p times 1 minus p. We worked that out before, and here it is again. And so the standard deviation of a binary variable is the square root of that. And so it's not all, so well, let's say it both ways. The variance is p times 1 minus p. So it's not all that surprising that the sample variance is going to be close to p hat times 1 minus p hat. Not quite. There's a fudge factor of n over n minus 1. Well, that's going to be close to 1, but yeah, if you start from our equation for s squared, in this case, we end up here. So f itself, the sample standard deviation, is going to be the square root of this. The standard error, that's s divided by the square root of n. Okay, so we take the square root of this, the right-hand side here. We divide by the square root of n. Well, that's going to cancel the square root of n that we get in the numerator. So after those things cancel, the square root of that divided by the square root of n minus 1. And the author on page 907 says it's not so terrible to use n here instead of n minus 1 because it won't make a whole lot of difference. Well, it won't make a whole lot of difference if n is really big. Well, so it's like what we said before in the general case for confidence intervals. But for binary variables, there's this shortcut for finding standard errors. Well, so next week we'll look at some examples, but except for talking about some limit theorems, we're getting close to the end of the material we're going to cover this quarter. Got to stop for today.